Hey guys! So this video is just meant to serve as a quick recap of what you guys saw in class of stress-strain curves. So for this entire video, we're going to be assuming we have some sort of bar specimen, like some sort of uniform cylinder with some length, original length L sub 0, and we're going to be applying some sort of equal and opposite force to both ends. So let's say we just pull it, right, with some force F. So what is stress and what is strain? Stress is going to be equal to the force divided by the cross-sectional area of the bar. And so since you're going to have stress in terms of a unit of force divided by a unit of area, the SI units for stress are going to be in pascals. Typically though, when we're working with real-life materials, the stress is going to be typically in the megapascals to gigapascals, as in like 10 to the 6th to 10 to the 9th pascals. So we're dealing with like a crap load of pascals. And so that's stress. What is strain? Strain can be seen as the amount of geometric deformation that occurs to the material because of our stress. There's a bajillion and one ways of measuring strain, but the one we're going to be most interested in for this course is just like a percent elongation kind of thing, where you have the strain is going to be equal to delta L, the change in length because of your pulling, over the original L sub 0, in which we can replace the delta L by the absolute value of the instantaneous length, L, like the length at any point in time, minus the original length, absolute value of that, over the original length. It's critical to note, though, that the strain is going to be unitless, because we have here a unit of length over a unit of length, so the units will cancel out, giving you a measurement that is unitless. Also, if you are deforming this thing elastically, as once you apply your stress and you release, the material will go back to its original length. If that's the case, you can use this equation here to relate stress and strain. So this here says that stress is going to be equal to strain times some sort of constant, which is denoted here as E. This is called Young's modulus, and it's an intensive property, which means that no matter what the geometry of your sample is, the Young's modulus for a certain type of material will always be the same. So like if you have copper, no matter how you cut your copper, it's always going to have the same Young's modulus. Right? Cool. So then what a stress-strain curve does is it measures stress as a function of strain, which means that on your y-axis, you're going to have your stress, and then on the x-axis, you'll have your strain. Another way of thinking about this is this plot measures the amount of stress that you need to get a certain type of strain. So let's say I have my material that's this long, and I wanted to get to, let's say, this long. How much stress will I need to apply to get the guy out this long? And also, if I can even do that. So if you think about it, if you have a bar like this, if you pull too much, well, it might break, right? It's like a rubber band. You pull too far, it might break. You can't just get all rubber bands from being this small to being this long. And this plot will take into account that also. So before we get into what the plot actually is, let's just take a look at this thing macroscopically. What happens when we apply a uniaxial tensile force, just pulling it, to some sort of bar? So in the beginning, we have, well, our bar, right? And we start pulling. So for little pulls, it's just going to be elastically deformed. As you pull a tiny, tiny bit, you release, and it just goes back to being what it was before. So this is for small pulls. It's just going to be the same length, elastic deformation. However, if you keep pulling and pulling and pulling, thinking about like a rubber band, right? If you pull too hard and you don't break it, it's going to be permanently deformed, like it's going to be permanently stretched, which we call here as plastic deformation. So if you stretch too far, it can become elongated, right? And then if you keep pulling after that, what you'll have going on is something called necking. So this is a phenomenon when your bar gets even longer, but it starts to thin out a little bit in the middle because the material in the middle is being moved to the ends. And then you keep on pulling some more because you feel like it, and the poor guy breaks. And that's what we call failure. So you can have some sort of, oh, sorry about that, some kind of broken bar like this. Failure. So the stress strain curve takes into account all these events that happen over the course of pulling your poor guy. So in the beginning, we have elastic deformation, correct? When we have elastic deformation, like we just saw, this equation is going to hold, where stress and strain are going to be linearly proportioned. So which means we're going to have a straight line. So this is the elastic deformation region from here, from 0 to some sort of epsilon of 1, right? And then after that, you have some sort of local maximum. You keep on pulling, and then because of necking, you'll reach some sort of another maximum, the global maximum in this case, and then the curve kind of goes back down, and then you fracture there, right? This entire region over here is deformation from 1, so epsilon sub 1 to say epsilon sub 2 here where it fails. This region is deformation, and this region here details elastic deformation. Cool. So then, from stress-strain curves, you can also get a bunch of information that tells you a lot about the sample itself. You can determine a bunch of materials properties just from this one curve. So the first one's kind of obvious. Well, we just look at this region here, the elastic region. We said that, okay, stress is going to be equal to Young's modulus times strain. So if you think about it as like y equals mx, the Young's modulus here is just the slope of the line. So if we take this and we take the slope of this, we can get Young's modulus. So E is going to be equal to the slope of this line. Cool. Also, what we can find out is this value here, known as the yield stress, which we often denote as sigma sub y for being yielding. That is the stress after which the material stops behaving elastically and starts behaving plastically. As in, like, you pull it any further, it's going to be permanently deformed. That we can just find out by, well, where the linear portion of this graph ends. And that value is going to correspond to the yield stress. Also, what we can find out is this point up here is going to be what we call the ultimate tensile stress. Ultimate tensile stress. I can't speak today. Which we sometimes denote as sigma sub UTS. UTS for being ultimate tensile stress. And that is the maximum amount of stress that you can possibly apply to this thing without it breaking. If you go any more, it is going to fail sometime up there. So that's your normal stress strain curve for a typical material. What happens though is that a lot of materials don't really follow this, as in, well, not all materials are normal. Some materials are made special, right? So let's say we have something like concrete, which is kind of interesting to note because concrete is really brittle. As in, if you do a uniaxial tensile stress on a bar of concrete, you'll have some elastic deformation, but you won't have plastic deformation, in the sense that after it reaches some really low yield strength, it's going to break. So if you have some sort of brittle material, like concrete, what you'll have is you just have stress and you have strain. You'll just have a straight line up, and then maybe some very small amounts of plastic deformation, and then you'll just break up there. So if you see any stress strain curves that looks like this, it's going to be a brittle material. Likewise, if you have something that's really ductile, like, say like a rubber band or something, rubber bands are kind of nice. If we plot the stress strain curve for a rubber band, it's going to have a really, 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 really large elastic region because you can just keep pulling the guy for a long time, actually. And then a pretty large plastic region, and then finally, failure over there somewhere. The last type of material that might be useful for this course is something that we call a ductile material. Let's say something like, okay, let's just say plastic wrap even. For plastic wrap, you don't really have much of elastic deformation, but you have a crap ton of plastic deformation. So what you have there is you'll have a graph that looks like this, where you have only a really small elastic region, a crap load of plastic region, and then finally, failure out there somewhere. Right? Cool. So this was just a really quick crash course in stress strain curves. If you didn't really follow what I said, just rewatch this a few times and you should be okay. Right? Cool. I'll see you guys later.